Welcome to Math 150, Section 2, Lecture 26. We're calling it 26 so it aligns with 2014 lecture, 2021. And what we're going to do today is talk about the root test, the integral test. We'll talk a little bit about alternating series and how careful you have to be when you have a sum involving both positive and negative terms. We're going to start off with a situation where the ratio test in some sense fails, so that at the end of the day we can say, aha, we have seen a situation where the root test beats the ratio test. It's not the greatest example because it's only a failure if you deliberately ignore a very simple fix to make the ratio test work, but it is technically a situation where the ratio test does not succeed. And it does allow us to talk about an interesting point. So consider the following. Let's let an be 2 to the negative n if n is odd, and 2 to the negative n plus 2, which is 4 times 2 to the negative n if n is even. So what quantity do we have to compute if we want to use the ratio test? We have to compute rho, and what is rho equal to?
We get n plus 1 over a to the n?
I'm sorry? A to the n plus 1 over
8.
So we look at an plus 1 over an. What is the difficulty in calculating this limit? What do you have to worry about? If an is 0. And in fact, you can't make this up. I was contacted by a teacher at Williamstown Elementary yesterday. Her students wanted to divide 0 by 0. And so she called me up and said, hey, let's do a quick Zoom. And so we talked about the issues of dividing by 0. Okay? We don't have that problem here. What else is going to be a little bit problematic for us when we want to try to calculate an plus 1 over an? When you look at what we have here, what's the issue? Wait, what should I substitute in for an plus 1? It depends. So this is like Lagrange multipliers. When we tried to solve problems with Lagrange multipliers, we often found that the best thing to do was to split it into several cases and do each case separately. So here's the case when lambda equals 0. Here's the case when x equals 0. And then you make sure that your cases are exhaustive, that you cover all possibilities. So case 1, n is even. I think it should be clear what case 2 will be. So if n is even, we have a to the n plus 1. So let's let n equal 2 times m as an even number. So a n plus 1, you get a 2m plus 1 over a 2m. So a 2m plus 1 is going to be 2 to the negative 2m plus 1 divided by 4 times 2 to the negative 2m. This is equal to 2 to the negative 1, so it's 1/2 times 2 to the negative 2m over 4 times 2 to the negative 2m. So we just get 1/8. Okay. This. Let's look at case 2. So n is odd. So let's say n is equal to 2m plus 1. So if we look at what's going on in that case, we have a of 2m plus 2 over a of 2m plus 1. So a 2m plus 2 is going to be 4 times 2 to the negative 2m plus 2 divided by 2 to the negative 2m plus 1. So it's going to be 4 times 2 to the negative 2 times 2 to the negative 2m divided by 2 to the negative 1, 2 to the negative 2m. The 2 to the negative 2m's cancel. 4 times 2 to the negative 2 is 1. So this is just equal to 2. So what does the ratio test tell us? Does it converge or diverge?
Diverge?
Why diverge?
Oh, no.
So why are you changing your mind?
Because they're different.
Right. The ratio test says if the limit exists, then if rho is greater than 1, it diverges. If rho equals 1, no information. If rho is 1, it converges. Does the limit exist? No, we can't use the ratio test. The limit does not exist. It's equal to, on anything we go through evens, it's equal to 2 if we go through the odds. So we can't use the ratio test. We can. We can just reorder them. Which terms would you like to group together? So we have all of these terms. Which terms would you like to add together? I claim if you look at the sequence and if you look at how it's defined, certain terms are screaming, please collect them. All the odds. So if you look at all the odds, we would have 1 over 2 plus 1 over 8 plus 1 over 32. And I could pull out a 1/2 from everything. And it's going to be 1 plus 1/2 squared plus 1/2 to the 4 plus 1/2 to the 6 in the algebra. Does that some converge or diverge? Converge. Why does it converge? Geometric, the ratio is 1/4. We can now look at the even terms. And we've got a 4, we'll pull the 4 of everything. And then when we start off, we have first n equals 2, so that'll give us 1/4. Then we have n equals 4, so you get 1/16 or 1/4 squared. Did I make a mistake? No. And then we'll have 1/4 cubed. And so on. I'm just writing it a little bit differently. Here I'm writing it as 1/2 squared, 1/2 to the 4th, 1/2 to the 6th. This is really just 1/4, 1/4 squared, 1/4 cubed. Does this series converge with hyper? Converge. It's converges for the same reason. It's also a geometric series with ratios important. So while the root test fails because it doesn't converge, it fails in such an easy way that we can fix it without any test. All we have to do is to say, let's look at the even and the odd terms separately. Okay. So we will see later that the root test is a little bit more powerful, but if this is the only way the root test wins, it's not a huge victory. Because in something like this, you can just split things up naturally. Now, this does open up a really good, interesting question. What do you do with a sum if you want to rearrange the terms? Can you add numbers in any order? Does it matter which way you add numbers? So is 3 plus 5 going to be the same as 5 plus 3? Yes. Can you add numbers in any order you want without changing the sum? No. So there's always a danger. So 0 over 0 is the danger. What's another danger in mathematics? What's symbol? Infinity. If you have infinitely many terms, then maybe what's okay to do finitely often is not necessarily okay to do infinitely. We actually saw with Fubini's theorem that we could have an example of a double sum, which you could smooth out to a double integral, where the order of adding matters. Horizontal vertical is not the same as vertical horizontal. The same is true for sum. That for some of the sums, we will get a different answer depending on the order in which we add. So what I want to do now is I want to give you an example where if I add things in a different way, I will get different answers. So the first is I want a sequence, I want a sum that diverges. Now, you're going to give me a sum that diverges for a stupid reason, a trivial reason. What's the trivial reason for a sum to diverge?
Oh, because it's A of n doesn't go to.
Yes, if A of n doesn't go to 0, it's not really that interesting that it diverges because it can't converge. So you could give me a geometric series where R is greater than or equal to 1. Aha, Professor Miller, diverges. Okay, there's not really an interesting divergence. So can you give me a series where the terms tend to 0 and it still diverges? So I want the terms going to 0, but the sum to be 1 over n. So I do 1 plus a half plus a third. I'll do a few plus 4. So this is the harmonic sum that diverges. So what I want to do now is I'm going to look at the alternating harmonic sum. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh, and so on. So the question is, does this converge or diverge? First of all, do you think it's positive, negative, or 0? Okay, why positive?
Because you start with like 1 and that's bigger than 1/2. And then 1/3 is bigger.
Good. So we know it has to be greater than 0. Could the infinite sum be greater than 1? Why not?
You're never gonna make up for the. Like, yeah.
Once we have 1, the negative 1/2 beats the 1/3, the negative 1/4 beats the 1/5. So we know it's got to be greater than 0 and less than 1. We now add in negative 1/2, we get to 1/2. Are we greater or less than a half? So we've got 1 minus a half, which is a half. Well, 1/3 beats 1/4, 1/5 beats 1/6. So everything from that point onward is positive. So we have to be greater than a half. We then add in 1/3, which brings us to 5/6. And now we see the next term is negative 1/4 beats 1/5. So we're less than 5/6. So when we go like this, we see that the gap between the upper and the lower is shrinking. And the more terms we add, the smaller the gap is going to be. It will converge to something. It actually converges to an extremely important, interesting number, which we will talk about later. So with this with this signing, the series converges. So we say the series is conditionally not absolutely convergent. And this is the alternating harmonic series. And to be absolutely convergent means if you put in absolute values, the series converges. This series does not converge if you put in absolute values because it's just a standard harmonic series. Conditionally convergent means in the order in which it's given, if you add, it will converge. Does anybody have a favorite number? 7. I need one more favorite number.
3.
3. Okay. What I'm going to do, and this is similar to the video that I sent you, which gave pi, is I'm going to reorder the way I add the terms, and I'm going to have it converge to 7, and then swing back and converge to 3, and then converge back to 7, and then converge back to 3. It's going to hop back and forth between the two. And what I'm going to do is I keep adding positive terms until I first exceed 7. And because the harmonic series diverges, we'll show in a little bit that all the odd terms have to go to infinity when you add them together. All the even terms have to go to negative infinity when you add them together. So I just keep adding odd terms until I break 7. Now what do? I want to get to 3, so I kept adding positive terms. 1 plus a third plus a fifth plus a 7 plus a 9. I keep going until I finally break 7. Now what do? So that's right. So now I subtract a half, a fourth, a sixth, an eighth, and I keep subtracting until I first get below 3. And now what do? Right, so I look at whatever was the last positive term I added. Maybe it was 1 over quadrillion and 3. Now I'd add 1 over quadrillion and 5, 1 over quadrillion and 7, 1 over quadrillion and 9. It will take a long time. But then I eventually exceed 7. Now what do? I subtract. And I do that until I'm first below 3. I keep going back and forth, back and forth. If I wanted it to converge to something, here I'm having it hop between 3 and 7. If I wanted it to converge to 3, I would keep adding positive terms until I first broke 3. And I would subtract terms until I just got below 3, then add positive terms. I can reorder the sum to get whatever number I want. This shows you how dangerous it is when you have something that converges conditionally, but not absolutely. Because it conditionally converges, but not absolutely converges, I can make the sum whatever I want. If you look at the sum of the even terms, 1/2, 1/4, 1/6, 1/8, it's actually just half the sum of the whole series, right? So if the initial series is plus infinity, if I look at the sum of just the evens, the sum of the evens is going to have to be negative infinity. Because the odds are always larger than the corresponding evens, the sum of the odds has to be positive infinity as well. So if I restrict myself to just the odds, it's plus infinity. If I restrict myself to just the evens down here, it's negative infinity. And so what really happens is I rearrange, I have infinity minus infinity. This is one of the things you are not allowed to do. You can't do infinity minus infinity. Okay, any questions about this? So this shows you how careful you have to be when you have things that are conditionally convergent but not absolutely convergent. Okay, so the alternating series, this is a great example to have on reserve. Yes? So depending on how you group things, you'll get different answers. Now, we gave a heuristic argument that it converges. Let's go to what you said and let's group things and show that it actually converges and get some sense of how quickly. So what I'm going to do is we will group terms together like this. So we have the sum, and it goes from 1 to infinity. I'll do that. I like to let it. 1 over 2n minus 1 minus 1 over 2n. So that's the odd term minus the next even term. How would I subtract those two numbers? How do you subtract two fractions? All comes down to algebra. How do I subtract two fractions? Yeah, so I would multiply this by 2n over 2n, this by 2n minus 1 over 2n minus 1. So we get 2n minus 2n minus 1. Well, that's just going to be the sum, and goes from 1 to infinity, of 1 over 2n minus 1 times 2n. approximately, what does the denominator look like when it gets large? Approximately. It looks approximately like 4n squared. So if I give you the sum of 1 over 4n squared, do you think this converges or diverges?
Or converges.
Converges. Why? What are you comparing it to?
1 over n.
1 over n squared. Now, I can do this a little bit more carefully. This is less than the sum n goes from 1 to infinity of 1 over 2n minus 1 squared. I make the denominator a little bit smaller if I replace 2 with 2n minus 1, which makes the expression a little bit larger. We saw this in the last class when we were trying to look at some of the ratios. That rather than doing the algebra that's given, if I do a little tweak like this, it makes things a little bit nicer. Oh, well, this is the sum of 1 over odd squared. Well, that's clearly less than the sum from 1 to infinity of 1 over n squared, summing over all the integers. And this converges. It's a p-series when p is greater than 2. Times p is greater than 1. So by grouping it in terms of 2 like this, we can see that the sum is going to be finite. And we can even get a little bit of a sense of what the size is. It kind of looks like the sum of the squares. All right, so this is a great example that really highlights the issues with alternating series. Okay, so we're going to do the ratio test now. Or not the ratio test, the root test. Do you want to do convergence or divergence? We did divergence last time. What would you like to do this time? Convergence, good. Because you actually had no choice because I told section 1 since they chose to do divergence because they wanted to do a different case, that you guys will have to do convergence. And this way, again, the algebra is extremely similar, but by looking at the other section, if you want to see a little bit more on this, you can see the other way too. Okay, so now it is the root test. So assume rho is the limit as n goes to infinity of the absolute value of an to the 1 over n. So this is the nth root of an. If rho is greater than 1, it diverges, rho equals 1, no information, and rho less than 1, it converges. So this should look extremely familiar, right? This should look a lot like the ratio test. Okay? So I'm going to sketch the proof. Let's assume rho is less than 1. So fix a small greater than 0 such that rho is less than 1 minus epsilon is less than 1. For all n greater than equal to n, we have an the 1 over n is going to be less than 1 minus epsilon. So let's just draw what's going on. Here's 1, here's rho, here's 1 minus epsilon. Because we converge to rho, if n is sufficiently large, we have to be extremely close to rho. You give me any tolerance, 100, 1,000, 1 million, 1 billion, 1 Google Plus. I've got to be within that distance of rho. Okay, well that means then that there's some separation between rho and 1. Rho is strictly less than 1. Choose a number such that 1 minus epsilon is outside that band, but still less than 1. And because the limit exists, then as n gets very, very, very large, this has to be very, very close to rho. Well, this is very, very close to rho. It's going to be less than 1 minus epsilon. Right. I don't like thinking about square roots, cube roots, fourth roots, fifth roots. If I tell you the square root of my number is 3, what are you thinking of? The square root of my number is 3. 9. The cube root of my number is 3. 27. Okay? So instead of saying a to the 1 over n is less than epsilon, how might you interpret this? How could you interpret this? Absolute value of an. So if an to the 1 over n is less than 1 minus epsilon, what can you tell me about an? So how would you do the algebra? How could you express an? Well, 1 minus epsilon to what power? The n power. Okay. So an is just less than 1 minus epsilon to the n. Any idea for comparison test now? Compare to, we know an is less than 1 minus epsilon to the n. What should we compare this to? So we're trying to show a convergence. Do you know any series whose terms look like 1 minus epsilon to a power? So the nth power. 1 minus epsilon, 1 minus epsilon squared, 1 minus epsilon cubed, 1 minus epsilon to the 4th. What kind of series is that? This is one of our go-to series. This is geometric. Compared to geometric with r equals 1 minus epsilon. Converges. So this is a sketch of why the root test works. And the root test and the ratio test, what they're really doing is they are doing the comparison for you under the hood. When you calculate rho, it's comparing it to a geometric series for you. And so it is amazing how often we are just going back to the geometric series. Okay. So the last part for today is the integral test. What class is this? Multivariable calculus. Right? It would be nice to actually do some calculus in a class called multivariable calculus. Right? We haven't been doing that much calculus. So there are certain things in mathematics where the name really gives away what you're going to do. You know, ratio test. If I'm asked to use the ratio test, I probably need a ratio somewhere. Root test, I need to take a root. What do you think is going to be involved in the integral test? It's going to be an integral. So the whole idea of the integral test is to determine whether or not a series converges or diverges by comparing it to an integral. And not only will you be able to get whether or not it converges or diverges, but you will also be able to get a good estimate for its size. Now we will assume an is either non-increasing or non-increasing. So what does it mean? What does it mean if you have a sequence that is non-increasing? What happens as you march down if it's non-increasing? Could the sequence, 7, 6, 3, 2, 8, -1? No, because it increased at one point. Non-increasing means it never, an plus 1 is never larger than an. So this means an plus 1 is always less equal to an. And non-decreasing means an plus 1 is always greater than equal to 8. Can someone give me a quantity associated to yourself that is non-decreasing? Age. Any Big Bang fans here? One of my favorite Big Bang moments is when Sheldon and Leonard are signing a roommate agreement. One of the clauses that Sheldon puts in is if either one of us ever invents a time machine, the very first place we will go when we invent it is right here in 5 seconds. And so Leonard signs and Sheldon goes, ah, that's disappointing. We can't go forward and backwards in time. We can only go in one direction. How about something associated to you that is neither non-increasing or non-decreasing throughout your life? Well, how many eyes you have almost surely is non-increasing. I could make that a decreasing sequence, but it would be my last lecture. How long your hair is. So I'm assuming everybody at some point in this class has had their hair cut either by a professional or an amateur or yourself. And so your hair length is going to alternate. Weight is another good example of something that is going to go in both directions. Most things are not strictly in one direction or the other. And so we'll assume an is non-increasing and have a function f of x such that an greater than or equal to f of x is greater than or equal to an plus 1. So we're going to assume that such a function exists. Most of the time, the way you find the function is you take the sequence an and you do a search and replace. And everywhere there's an n, you put an x and you call that your function. And that almost always works. So if I give you the function 1 over n, what would you try for your function? 1 over x. And then what I'm going to do is I'm going to just do an analysis, and then from the analysis we'll extract the result. 0, 1, 2, 3, 4. So let's look at the sum of the first 4 terms. So here I have a rectangle of height a1. The base has length 1, so the area of this rectangle is just a1. Then over here I have a rectangle of height a2, so the area of that rectangle is just a2. And this would be a3, and this would be a4. And because my function is sandwiched between an and an plus 1, it looks something like this. And so if you look at the integral under f, the area under the curve, it's clearly going to be less than all of this. Right? And what's a little bit annoying is I have to go all the way up to the 5th term. I have to integrate all the way up to 5 when I'm doing 4 terms. So I would have the integral from 1 to n plus 1 of f of x dx would be less than equal to the sum that goes from 1 to n of a. So I can get a lower bound for the sum by doing this integral. Now I'm going to get an upper bound for the sum with this integral, with a little bit of a twist. Instead of going to the right, I'm going to start off by going to the left. So my first box, I'm going to draw this. The second box, instead of having a2 go to the right, I'm going to have a2 come to the left. And this will be my A2. This will be my A3. This will be my A4. And so now, if I integrate from 1 to 4 and add in the value A1, it's going to be an upper bound. So this sum will be less than or equal to A1 plus the integral from 1 to n of f of x dx. Okay. So let's just see how much they really differ on. So one thing that's a little bit annoying is that they're not integrals over the same range. But as n gets very, very large, it's almost the same range. And so if we just write things a little bit more carefully, we get the following. So we would get the integral from n to n plus 1 f of x dx plus the integral from 1 to n of f of x dx is less than equal to the sum k equals 1 to n of ak less than equal to the integral from 1 to n of f of x dx plus a1. And the real meat is this part over here. Is the sum k goes from 1 to n of ak is approximately the integral from 1 to n of f of x dx. How much am I off by? If you add a1, it's now an upper bound. For the true lower bound, I have this integral from n to n plus 1. Well, in many cases, your sequence an is going to be tending to 0. And so if the a's are tending to 0, then f is tending to 0. So in many cases, this will tend to 0. If your sequence, however, is strictly decreasing, then you have a bound in this as well. Because your function is going to be at most an. So this is at most an as assumed decreasing. There's a similar set of results if you assume instead that the sequence is increasing. We're doing the case when the sequence is decreasing. Yes?
What is that most an?
This integral. It has length 1, and because f of x satisfies an is greater than or equal to f of x is greater than or equal to an plus 1. And so I'll write this down. For n less than or equal to x less than or equal to n plus 1, have an greater than or equal to f of x greater than or equal to an plus 1. So when you take x equals n, it's an. When you take x equals n plus 1, it's an plus 1. And we're assuming our function is decreasing that region. Or at least, you could actually allow f to have some oscillation. That would be fine. But you still just need an is always greater than or equal to, and an plus 1 is always less than or equal to on these intervals. So as x goes from n to n plus 1, an is an upper bound, an plus 1 is the lower bound. So it's at most an plus 1. It's at least an minus 1. So if we want, I'm sorry, an plus 1. So if we wanted a lower bound, that's what we would use for the lower bound. It's at least an plus 1. So the value of this sum is very close to the value of this integral. It differs by at most a1 for the upper bound or an plus 1 for the lower bound. So this is the integral test. So if this integral, if you look at the limit at n goes to infinity of the integral from 1 to n f of x dx, if this is infinity, then the sum diverges. And if it's finite, the sum converges. And not only does the sum converge, but we have a really good sense of the value of that sum. Okay. Any questions? questions about the integral test before we apply it? So we're going to apply it in two different cases. The first, let's do a sum that diverges. So what's our favorite divergent sum that we like? 1 over n. The harmonic series is a great example. We know it diverges. How quickly does it diverge? It turns out it goes very, very slowly. So if an equals 1 over n, I need an f of x. And again, search for place, n becomes x. Let's try f of x equals 1 over x. And clearly that's going to satisfy the constraints that I need. And so I get that the sum k goes from 1 to n of 1 over k is approximately the integral from 1 to n of 1 over x dx. All right, what function has derivative 1 over x? Natural log. And once you're into college, you write the natural log as log. And so it's the natural log of x evaluated at 1 and n. So it's the log of n minus 1. Well, the log of 1 is just 0. And we'll review log laws on Monday as part of the general review. So this tells us that the sum diverges, because as n gets larger and larger and larger, log n goes off to infinity. But more than just telling us it diverges, it gives us an idea of how quickly. So if I take n equals e to the 100, what is e to the, how big is e to the 100? Pretty big. What is the log of e to the 100? Yeah, it's 100. Let's see which order Mathematica wants to do things. Okay. Okay, so e to the 100 is approximately 2.6 times 10 to the 43. Okay, that's a big number. Its logarithm is 100. E to the 1,000, what's the log of e to the 1,000? Oh. It's approximately 2 times 10 to the 434. Now, 10 to the 100 is more than all the subatomic particles in the universe. So if everything in the universe was a universe, that gives you on the order of 10 to the 200. That gives you a sense of just how bad 10 to the 400 is. Right? When you have huge numbers, you always want to put them in a meaningful context. One of the best quotes I ever heard is this: radiation is so energetic, it would go through a lead shield running from the sun to Pluto. Okay, we're not stopping it. This is energetic radiation. More than a universe of universes, this is huge. Yet the log of e to the 1,000 is only 1,000. That shows you how slowly this function is growing. When we take that many terms, we've just finally hit 4 digits. We have no chance of actually numerically just adding up enough numbers to see it break 1,000. Okay, any questions about this example? We have time for one more example. This one's a little bit hard. I want to study n factorial of n minus 1, n minus 2, blah, 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 3 times 2 times 1. How big is n factorial? I love being able to end this sentence in a grammatically correct manner with a question mark followed by a factorial. How can I attack this using what we've done? Everything we've done involves sequences and series and sums. What can I do? How can I handle n factorial? Logarithms, right? Pavlovian response. Whenever you see a product, it is a logarithm. So the log of n factorial is the log of 1 plus the log of 2 plus the log of n. And we'll talk about this on Monday. The log of a product is the sum of the logs. What should this be approximately equal to? Well, this looks like a sum. My nth term is log of n. Want to give me a thought for what f of x should be? What should I try for f of x? Log x. So let's try log of x. So this should be approximately the integral from 1 to n of the log of x dx. Now, as an extra credit homework problem, I asked you to compute a while ago what is the antiderivative of log of x. And it's x log x minus x. And again, I'm not expecting you to be able to do this, but what can you do if I give this to you? You could, of course, blindly assume that I'm correct, but you can check it by just taking the derivative. And if you take the derivative, you'll see it does work. So when I put an n, you get n log n minus n, minus, well, the log of 1 is 0. So it's going to be minus negative 1. So the log of n factorial is approximately this. Well, I can then recover by exponentiating. So n factorial is approximately e to the n log n minus n plus 1. So that's e to the n log n, e to the minus n times e. E to the n log n is the same as e to the log of n to the n, e to the minus n e. And we will review the laws of exponents on Monday. And basically using e to the ab is the same as e to the a, all of that to the bth power. And we'll review that on Monday. What is e to the log of n? So what is e to the log of n? It's just n. What is the log of n? The log of n is how many powers of e do I need to get n? If I raise e by the powers of e that I need to get n, I get n. So I get n to the n, e to the minus n times e. And that's a really good approximation for n factorial. With a little bit more work, you can show n factorial is about n to the n, e to the minus n, square root of 2 pi. And with a little bit of work, we could actually get a better sense of what the error term is here. But this is a good enough job to give us pretty cheaply a sense of the true size of n factorial. And again, we could make this a little bit better, but we're already seeing n factorial is like n to the n, e to the minus n. If I want to do ratio test or root test now, wow, this is going fast. If I want to take the nth root is essentially n over e. It's going off to infinity. N factorial is growing fast. Okay, so this finishes the introduction to the root test and the integral test. Next class, we're going to start doing the Taylor series, and that's when we're going to start using a lot of these tests that we've been using to start writing down sequences that we can then use to form a series. And the hope is that these series will do a really good job of approximating our functions. And we saw with Newton's method just how much you can do with just the first derivative. All right, so this is a good place to stop.